Okay, here. If you try to just put a channel for acetylcholine here in the vesicle, that is very ineffective because you should have more acetylcholine inside of the vesicle than out in the cytoplasm. So if you just plug a channel in there, you're just going to lose your acetylcholine that is going to go down its concentration gradient by diffusion, and you don't want that, right? You want to accumulate acetylcholine inside of your vesicle because you're going to need it once you need to activate your muscle, right? You need for exocytosis. So what's the trick that allows this to happen is that first you're going to get something inside of this vesicle that is going to create a gradient. In this case, is a proton gradient. How do you get a proton gradient? Well, you stick here a proton pump. Okay, so a proton pump is going to push protons to the inside of these vesicles. What's going to happen to the pH inside of the vesicle? Going to go down, more acidic, right? pH is going to, the environment here is going to get more acidic. You have a concentration of protons there. So this sodium, not sodium, sorry, this is a proton pump. This proton pump is going to use ATP to push protons against their concentration gradient to get a lot of protons inside of this vesicle. So now that you have a high concentration gradients of protons here, you can use that potential energy to push another system over here. So this transmembrane protein right there, this channel right there, is called an antiport channel. Okay, so the way that this channel is going to work is that it's going to exchange one proton that is going to go naturally down its concentration gradient, right? It's going to exchange one proton for one acetylcholine. Okay, and this is how you get to pack acetylcholine against this concentration gradient inside of those vesicles. Does that make sense to everyone? Do we have a question about that? Is it clear? Yeah.
So proton pump helps supplement the antiport, which causes one proton for one acetyl.
Yes, the proton pump here is packing up protons inside of the vesicle. Okay, it's using ATP to do that. So this proton pump is a primary, what do you call that? Primary transport mechanism, because it's directly using ATP. And then this antiport transmembrane protein right there, what do you call that one? Secondary, right? Secondary in terms of energy usage, because if you don't have this gradient right here, then this pump, this transmembrane channel is not going to work. Okay, it's an antiport that depends on the energy that was pumped by the proton pump. Okay, everybody clear with that one? All right, cool. Okay, so what happens once you dump acetylcholine in this space that is called the synapse, right? So what happens here is that acetylcholine is your neurotransmitter at the neuromuscular junction. It is going to find a receptor on the membrane of this muscle fiber right there, okay? So this receptor here is called a ligand-gated channel. It needs something of a ligand to bind to it, so it will open, okay? It is mainly a sodium channel. A little bit of potassium may leak through it, but it's mainly a sodium channel. Sodium, ligand-gated sodium channel, okay? What is the ligand? Acetylcholine, that's your neurotransmitter. That's your ligand for the channel, okay? So what's going to happen here? Once you dump acetylcholine in this space, it will diffuse quickly and find the receptor sites that is going to bind in this channel. Once it binds, it's going to open the channel. And once it remains bound, the channel is going to remain open. Okay? Channel is going to remain open. So what happens here, you're going to have a flood of sodium to the inside of the cell. Some potassium may diffuse out, but the main thing is the sodium that gets to the inside of the cell. That's going to cause what? Depolarization of your membrane, right? Depolarization of the membrane here. That depolarization is going to be transmitted to the other side here of the membrane, okay? And is going to become here an action potential in this, like right on this membrane right there. Okay, so this is at your muscle. This is at the muscle sarcolemma. Sarcolemma is the plasma membrane of your muscle, right? Okay, so what's going to happen here? So we got that. Here we see the depolarization of that membrane is also called end plate potential. Okay, the same thing as the polarization of your muscle membrane. Okay, now that is going to create the muscle action potential. Now the whole idea here is that first you had this chemical signal that bound here to the ligand-gated channel, and then it was transformed to electrical signal that became your action potential in your muscle. Does that make sense? Yeah. Okay. So now what's going to happen? This action potential is going to propagate, right? Okay, so here you have another picture, just a better picture of your ligand-gated channel, right? You're going to allow sodium in, a little bit of potassium out, it mainly is the sodium in. So now that channel is going to stay open while it is bound to its ligand, which is acetylcholine. You don't want the channel open all the time, right? You want just to send a signal, then stop sending the signal, okay? So in order to stop sending the signal, you have to degrade that ligand that was stuck to that channel. The ligand is acetylcholine. How do you break down acetylcholine? Cholinesterase. Use an enzyme for that, right? There is an enzyme for that. If it is an enzyme, ends up in ACE. Just get the name of the molecule, acetylcholine, put an ACE at the end. That's the enzyme that breaks down acetylcholine. So acetylcholinesterase is right there at the synapse, so it breaks down acetylcholine. There is one other way that you can get rid of acetylcholine. It's by diffusion out of that synapse. Okay, but the main mechanism is by enzyme degradation. Once the ligand is not there, the channel will close. Look, this channel does not have an inactivation ball. It just closes. It's either open or it's closed. Okay. Okay, so with this action potential, when it goes down the membrane and it reaches the T-tubule, right, that goes inside that sarcomere structure, right? When it reaches the T-tubule, it is going to communicate with the sarcoplasmic reticulum. What is it kept inside of that sarcoplasmic reticulum? Calcium. Everybody got calcium in your heads? Yeah. Calcium. How many positive charges in the calcium? 2. That's not that important to know, but just in case, all right? Calcium channel that is voltage gated is going to open. Calcium is going to come out of the sarcoplasmic reticulum and interact with a specific protein that is associated with your thin filament. What is that protein? Is it troponin? Okay, how many people think it's troponin? One person, okay. How many people think it's something else? Okay, how many people have no clue what I'm talking about? There you go. Oh. All right, so let's draw it out here, okay? When something doesn't make sense, try to draw it out and tell a story about it. It might make a little more sense, all right? So remember you have those thin filaments that are like that. What is that thing? Thin filament is actin. A couple of them that intertwine like that, right? Thin filament is actin. On this actin, you have these globular looking proteins that are protein, right, is associated with it, like this, like anchor. It anchors things to it. What's the name of that protein? troponin. And then you have this other protein that is associated, oops, that doesn't go like that. Okay, this other protein that is also filamentous protein is also string that is blocking the site in which myosin can attach the head. That protein is called what? Oh, green again. Okay, I'll put a different color. This guy is blue, okay? What's the name of that filamentous protein? Tropomyosin. Down here. Tropomyosin. All right. So that blocks the site in which myosin can attach its head. Once calcium goes in here, it associates with troponin and it shifts the conformation of that anchor, then is going to expose the binding site here on actin. Okay, it's going to expose it to what? Myosin head. Myosin head is going to attach to it. Okay. Now, when you're talking about striated muscle fiber, you're going to have to use ATP, right, to contract the muscle. You're going to remember about those sliding filaments, right? You're going to have to use ATP to attach the muscle. Now, you're going to have to remember the cycle of ATP usage on that myosin head, right? And about the stroke, the power stroke of the myosin head. You got to remember all that, okay? So make sure you totally understand that. ATP gets into the myosin head. Myosin has some ATPase activity, right? When ATP is bound, there's a certain conformation, and then it hydrolyzes the ATP, and then it bends the head. That's the power stroke. The bends the head when it's attached to your actin, right? Then the ADP dissociates, and then this thing comes off, right? Because it's going to bind another ATP. It's going to cock the head again, bind again, drop the and do power stroke again, and going to continue on that cycle using ATP directly. That's an important point to remember, because this is one very important difference between skeletal muscle contraction and smooth muscle contraction that we see today. Okay? So everybody's clear with those signals and usage of ATP, myosin actin interaction. Everybody's clear with that, right? All right, so let's go ahead here. So now we are discussing on where the energy comes from to power the muscle, right? So we left off saying that some muscles like to use glucose. Some other muscles like to use oxidative phosphorylation or aerobic type of energy source, right? And there are differences in these muscles' actions and muscle function, okay? So we mentioned that if you have a muscle that mainly uses glucose, that's a glycolytic muscle. The glucose is like right in its name, right? So in order for you to use glucose as an energy source, it needs to split that glucose that is a 6-carbon molecule. It needs to split into 2 3-carbon molecules of pyruvate. Okay? So in order to do that, you have to break down some covalent bonds. Like right there. Here's a covalent bond, here's a covalent bond. There are actually 2 covalent bonds that need to be broken. And those 2 covalent bonds carry a lot of energy, okay? Breaking one of these bonds has enough energy to put a phosphate on ADP. You see that? Breaking one bond gives you enough energy to put a phosphate on ADP. If you break 2 bonds, that's going to give you enough energy to put how many phosphates on how many ADPs? 2. Dos. Do. Dois. How many languages can you say 2? All right, so you have here 2 bonds that are broken. You have here two ADPs that can get two phosphates, and you can end up with two ATPs, right? When you break that bond, you have electrons that were shared over there. When you break the bond, the electrons gotta go somewhere. They don't just disappear. Where do they go? Not like magic, right? Sometimes we want them to just disappear, but they don't. Where do they go? No, they don't get together. They don't like to get together. They're two negative charges, they gotta go somewhere. But that's a good thought. They could get together and just go. They don't. What happens to the electrons? Take a guess. All right, let's just talk about the story. If you want to send someone somewhere, what do you do with them? Huh? I got time. I got time. What am I talking about? How are you going to get rid of these electrons? They cannot be floating around, or they can become free radicals. You don't want free radicals. Yeah, two.
Other,
That's a good guess, yes. Huh? No, not two protons, no. Well, they kind of go like protons. The electrons never go by themselves, right? Do you want me to tell you what happens? No? All right, tell me what happens then. If you have to carry something somewhere, what do you use? You're using the energy to make a phosphate bond to create ATP. By the way, that is called substrate level phosphorylation. Fancy term that you have to know? Yes, substrate level, because here is the substrate, right? Substrate level phosphorylation. All right, so substrate. What happened to the electrons? Are they going to be carried away somewhere? Guess what's going to do that? Something really dumb. It's called an electron carrier. I know, right? Electron carrier. You have several of them in the cell. In this case here, your electron carrier is called NAD plus. Nicotinamide adenine dinucleotide. Don't say that 5 times quickly. NAD plus. It has a plus charge right there. It's telling you, look, I have a plus charge. I can get a negative charge and become neutral, right? Negative charge never goes out by itself. So what this thing is gonna get is gonna be a hydrogen, okay? That is gonna carry, the electron. So NAD plus, one NAD plus picks up one pair of electrons that came from one bond, becomes an NADH. You have two bonds, so you're going to pick up two pair of electrons, and you're going to have two NADH. So this guy here is your electron carrier. It carries the electrons. They came out of the bond because the bond was used for energy. You need ATP, okay? What's going to happen? This guy here now, can you just keep the electron by itself forever? Well, it could. The problem is that it's useless if it keeps the electron because then it cannot do its job. Its job is to carry electrons somewhere. It needs to carry the electron somewhere, and then it needs to dump the electron somewhere to come back and pick up some more electrons because this muscle is working and it only has glucose to use for energy. So this guy here has to be available, okay? Where is it going to dump those electrons? Or those protons, right? Where is it going to dump it? If you have mitochondria around and oxygen available, it's going to go straight to the mitochondria and dump it there. Okay? You're going to get like oxidative phosphorylation. That's the job of the mitochondria. Oxidative phosphorylation using oxygen, that's why on its name. Oxidative phosphorylation is going to give you a lot of ATP energy. But look, where is the mitochondria here? It's not there. So now these electron carriers have a problem. They cannot dump those electrons on mitochondria because it's just not there. Okay? What's it going to do? You got to find something else to dump the electrons. It's going to find a double bond somewhere that it can break, okay, and make a single bond out of it and dump some electrons like that. You got to get rid of the electrons, okay? The only thing that it finds around that it can do that is this guy here, pyruvate. Where did the pyruvate come from? Glucose. So how many pyruvates you have here? 2 pyruvates, because you had one glucose, it broke down into 2 pyruvates. Now this pyruvate, oh, look at that, it has a double bond right there. Okay? NADH goes there, reacts with this double bond, breaks this double bond, it makes a hydroxyl group out of it, and with that, it dumps its electrons right there. So your pyruvate now became your electron scavenger. That's the garbage dump for electrons in case you cannot dump it in the mitochondria. Okay? That recovered the state of NAD back to NAD+. So now we can do its job again, which is pick up more electrons from more glucose molecules. Does that make sense? It should make sense, right? Now, this can go on as long as you have pyruvate available to pick up this electron, right? The problem here is that this guy here is a molecule of lactate, which is also called lactic acid. And if you accumulate a lot of it inside your muscle, something is going to happen. The pH of the muscle is going to go down. It's going to become more acidic. It's going to mess up the metabolism of that muscle. The proteins don't like to work in a very acidic pH. So your muscle is going to start having problems. Okay? You cannot keep lactate around for too long. Okay? So there is only a certain period of time that you can use this type of energy source, right? But this is what happens when you are using glucose for energy in a muscle cell. Okay, you're going to use this energy, this electron carrier to pick up the electrons from the bonds, and then it's going to dump the electrons on this product in order to recover its useful conformation. Okay, so now what's going to happen to the lactate that is in the muscle? Well, it's not going to stay there forever, and you're not going to be exercising forever either in the anaerobic state. So let's say you're done with that quick exercise, so now you're kind of relaxing. Lactate is going to diffuse out, it's going to come out, okay, come out of the muscle. It's going to get into the circulation. It's going to end up in the liver. So in the liver is very, very good with metabolic tricks. Okay, the liver loves to do a lot of metabolism stuff, right? So lactate gets into the liver. The liver has an enzyme that can convert the lactate back to pyruvate. Why didn't the muscle do that? It was busy, but it doesn't have the enzyme. Okay, it doesn't have the enzyme. The liver has it. So lactate gets into the liver, it gets converted to pyruvate again. And what's going to happen to pyruvate? What is the fate of pyruvate here? Well, many things can happen to pyruvate. Some of it can be used in mitochondrial function to produce energy, right? Some of it can be converted back to glucose. Do you know the name of that thing? How you convert pyruvate back to glucose? What would you call it? Yeah. Anabolism, that's a good overview view of it. Specifically, how do you call this anabolic process? It starts with a G. You're creating glucose. No, that you're breaking down glucose. Glycolysis is breaking down lysis of glucose. Yes, gluconeogenesis. Gluconeogenesis, that's the process from pyruvate back to glucose in the liver, okay? Gluconeogenesis in the liver. All right. Then glucose gets back in the blood, and then it can go back to your muscle, and then once it goes back to the muscle, then it can be used up again. And then you form this cycle here going on. Look at this. Muscle is using glucose for energy. Glucose is broken down to pyruvate and then to lactate. Lactate goes rushing to the liver. Liver converts it to pyruvate, that converts it to glucose, and then it gets back to the muscle. What do you call that runaround cycle? Exactly. That's the Cori cycle. That's right there. Got it? Cori cycle? Cori cycle. All right. So you know all about the Cori cycle now. Good. All right. So here, now talking about more energy that is used in usage of muscles, right? So we have here energy systems used during the sports. So you can have aerobic endurance, or you can also have anaerobic thing, okay? When you talk about aerobic endurance, so those are muscles that can use oxygen, and they can have a lot of mitochondria, right? They're going to use up their oxygen, and they're going to be fatigue resistant if you have enough endurance, right? And you can keep on using that muscle for a long time, for hours. So the example here is that if you're trained, for example, to run long distance, like marathon runner, then you're using these aerobic muscles, aerobic endurance muscles. Now, if you just picture in your head what these muscles look like, first they have to have a lot of oxygen, right? And the molecule that holds on to oxygen in the muscle is called myoglobin, okay? Myoglobin has a stronger grab on oxygen than hemoglobin. Hemoglobin is in the blood, right? So when blood gets to the muscle, myoglobin is going to steal that oxygen to itself and it's going to keep it inside the muscle, right? So when the muscle is working, this myoglobin is going to use that oxygen for the function of the mitochondria, because the oxygen is your ultimate electron acceptor, okay? So when mitochondria is working with all the electron transport chain and producing ATP, when it comes to the end of the chain, you got to dump those electrons somewhere. It dumps into the oxygen, okay? So you absolutely need oxygen for mitochondrial function. Now, these muscle fibers here, you can imagine they have to have a lot of myoglobin, a lot of oxygen, so they look really red, and they have to have a lot of mitochondria, right? So red with the myoglobin, full of oxygen, and it has to have plenty of blood supply. So you're going to have a lot of blood supply to these muscles, okay? A lot of blood, a lot of redness to the muscle. Okay, that's the red meat, okay? So this is the aerobic endurance. It can last for hours. Now, when you talk about anaerobic, that means without the use of oxygen. So those muscles, they're not going to be with a lot of proportional blood vessels, right? So they're going to look not as red. They're going to be like either pinkish or whitish, right? And the source of energy is going to be ATP that is stored in there, but ATP is used up very quickly. So ATP is like 6 seconds of energy is ATP. The other source of energy that is stored in this muscle is in creatine phosphate. Remember, the bond of phosphate to creatine is a higher energy than the bond of phosphate to ADP. Okay, so creatine phosphate bond can donate the energy to make ATP at substrate level phosphorylation. There's all the substrate going on here, right? All right. Now, when this storage ends, the muscle itself has stored glucose in the form of glycogen, right? So 2 tissues in the body can store glycogen. One of them is your muscle, the other one is your liver. The muscle is very selfish. It keeps the glycogen to itself. It's not going to share glucose with the rest of the body. It's not that it doesn't want to, it just doesn't have the enzyme for that. The liver does, okay? But here we're talking about glycogen storage in the muscle. So the muscle can cut little pieces of that glycogen that become glucose molecules and then use the glucose for anaerobic usage, right? Now the muscles that are used for with this type of energy, they are fast acting, but they fatigue very quickly, okay, because they run out of energy very quickly, as you can see here, right? In comparison to the muscles that are using aerobic respiration for energy, they can go on for hours and hours, depending on how much endurance training that person has, right? Now, here you have ATP, your creatine phosphate, your glycogen, and then here you have prolonged duration when you are using your mitochondrial function for aerobic respiration. Here is your first question. Yay. Okay. A sprinter is likely to depend on what kind of respiration to generate ATP. And then a Tour of France cyclist. Tour of France, it takes forever. Anybody do cycling here? Yeah, it's fun, right? Cycling is a lot of fun. So you need to have a lot of endurance for a long time. So what is the type of energy that you're using here for a sprinter in comparison to a Tour of France? Okay, so the sprinter needs energy quickly, and it is not with the help of mitochondria, so that's anaerobic energy. And then the Tour of France cyclist needs the mitochondria, right? And just for fun here, I had to put this little video, if I can go there. All right, muscle fatigue. Here is the pointer, yeah. So what is happening here? You are sending a signal from your brain to your muscle. You're sending a signal for it to contract. And then your muscles are failing you. They are not contracting. But you really want them to contract. And it's just not working. Okay? When you're totally exhausted, something is happening physiologically with your muscle that you just can't contract it anymore. Like if you go lifting weights, I tell you, I don't like to lift weights. I think it's dumbbell thing. That I really think it's dumb, but it's necessary. It's a type of it's necessary. But I see also why, right? So you are lifting those weights, like it's back exercise, you're pulling down those weights, and my back is hurting, and I can't take it anymore. And then at one point I'm like, oh, it's like almost total tetanus here. And they're like, I did a freaking thing. I don't want to do this anymore. And then this pain and the pain, like, oh man, it's like that's fatigue, right? What is causing fatigue? Several things are causing the fatigue, right? We used to think there was just the lactic acid accumulation, but it's not. Okay, other things are happening. We don't really understand fully what causes fatigue, but we know it happens. For sure it happens, right? Possible causes here of fatigue. First thing is ionic imbalance. So all the signal you're sending to your muscle, you're messing up, you're opening your sodium channels, potassium channels, calcium channels, and those channels are just like open, and those ions are going back and forth somewhere, and that can disrupt this membrane potential of the muscle. Of course, that's the whole job of the action potential. But if you do too much of it at once, that's not good. Too much of anything is not good, right? Except for money. Too much money, I think, is good. Anyway, so talking about muscle physiology, right? Another thing can happen here: increase concentration of inorganic phosphate. Where is this inorganic phosphate coming from? ATP and also from creatine phosphate, right? So creatine phosphate, you can break this bond, ATP will break that bond, and then you accumulate a lot of creatine phosphate. And what's going to happen is that your concentration of ATP, of course, is going to be depleted. When your concentration of ATP gets depleted, not only you're going to have here a lot of inorganic phosphate, but you're also going to have increased levels of magnesium, because ATP binds to magnesium, but ADP doesn't. So that's another imbalance in this ionic imbalance that you can have that can cause muscle fatigue. Okay? Now, lower levels of glycogen, that's another possible cause of muscle fatigue. And whenever you have the time, click on this video here and you'll see what happens in case of extreme muscle fatigue. Have you seen those marathon runners that just a few meters before the finish line, then their muscles can't take anymore, and they're like, they look like they're totally having a seizure and trying to get into the muscle. That's when they're like crawling on the floor. Like, it's so sad. I want to have the energy to run a marathon sometime in my life, but I don't. Okay. And then what did, yes. Right? I need to replenish the levels of oxygen that got depleted in the muscle. So that once you relax and you're still tired, like you're gonna be like, hyperventilating for quite some time because you need to put a lot of oxygen in your hemoglobin that has to shift it to the myoglobin and replenish your myoglobin in your muscle. You have to get rid of the lactic acid that build up, right? Your pH of the muscle got low, so now you gotta get rid of the lactic acid. So Cori cycle has to come into action. Also, you have to replenish the glycogen stores of the muscle, right? So a bit of hot chocolate is well, too much sugar, but a little bit of complex sugar, complex carbohydrates are good for that. Okay, now ATP and creatine phosphate levels also need to be replenished. So after you exercise, usually you're going to be like tired for quite some time. And also you need to regulate the temperature, your body temperature, because the muscles produce a lot of heat, right? And that's another reason for you to be breathing heavily after exercise, because you're really evaporating a lot of water, and the water takes away the heat from your body. Okay, so this type of recovery period after exercise is called excess post-exercise oxygen consumption, or EPOC. It used to be called oxygen debt, which I like a bit more, although I have always trouble pronouncing the word debt. The B is silent, right? Debt, not debt. Okay, so oxygen debt. So here, another question. Which of the following is not a fatigue-producing factor in moderate exercise? So here, lack of ATP is not directly producing fatigue, right? What is producing fatigue is excess of inorganic phosphate that came from the ATP, but not directly the lack of ATP itself. Damaged sarcoplasmic reticulum, that hurts. That produces fatigue, right? Intuitively, you say that hurts. Okay. Okay. So force of muscle contraction. So what is contributing to the force of muscle contraction? So first you have to see how many fibers are being involved in this contraction. So that is called recruitment. So recruitment of fibers, or recruitment of numbers of motor units that are in the muscle. Okay. Also the size of the fiber size of the muscle matters for force of muscle contraction. I mean, that's very obvious, right? The bigger the muscle, the more myofibrils you're going to have in the muscle fiber, and that is called hypertrophy. So exercise is going to cause your muscles to bulge, so you get a hypertrophy, bigger muscle, hyper for bigger, hypertrophy. Okay. Frequency of stimulation of the muscle, right? So if you stimulate it frequently, you can develop a greater force. Okay. And also degree of the muscle stretch. This one is interesting because the muscle has to be only a certain amount is stretched or relaxed in a certain way to give you maximum force. And the number here is between 80 and 120% of the stretch of the muscle. So let's see what happens here. So this just to give you a picture of these 4 factors. Right? So here, degree of muscle stretch. So if your muscle is quite contracted and you want to contract it more, it's not very effective. If your muscle is very relaxed and you're trying to contract it, well, there are not enough binding sites here for myosin, so that's not really very effective either. So you have to be in this Goldilocks zone of just right amount of relaxation or contraction. That's why I put a picture of Goldilocks over there. You have to be at this zone that allows for maximum contraction and force. Okay, and another question. Isometric contraction come into play when an individual is, what is isometric? Same what? When you maintain upright posture, you're not really changing the contraction of the size of the muscle. So contraction, velocity, and duration. So that is that's going to depend on the type of muscle fiber, also on the load, and on how many fibers are involved. Okay? Now, the type of muscle fiber, it has to do with what type of enzyme you have at the myosin head, because the myosin head is the part that hydrolyzes ATP. So depending on how quickly the myosin can hydrolyze the ATP, that's how fast you can move that muscle, right? Now, this involves the speed of contraction. You also have metabolic pathways of contraction. So glycolytic fibers are faster than oxidative fibers. Okay, glycolytic fibers are usually faster and more powerful, right, than oxidative fibers. So type of fibers, you can have slow oxidative, fast oxidative, and then fast glycolytic. You have a lot of fibers and it gets to be so confusing. So I just want you to get a ballpark idea of what these fibers are doing, okay? Most of your muscles contain a mixture of all of those, depending on what's the purpose that you're using the muscle for. So you're going to be recruiting some of those or most of them. It depends on what you're using the muscle for. So here, all fibers in one motor unit that is coordinated by one motor neuron, those are of the same type. Okay, so you're going to have several motor neurons if you have several types of fibers in your muscle. So here, examples here. Slow oxidative fiber. Oxidative is telling you it's using oxygen. Okay, so slow oxidative, that is low intensity but endurance activity, right? Like something that you have to do like all day long, like maintain your posture so you don't fall off the chair. That's slow oxidative fibers. They are usually low fatigue. They're resistant to fatigue. And then you have fast oxidative fibers. Those are your medium intensity, also oxidative with oxygen, right? So this is going to be like sprinting or walking, right? And then you have fast glycolytic fibers. Those are for short-term, very intense stuff, right? So this is like hitting a baseball or punching something, right? A pillow, okay. All right, so this chart is FYI, so if you want to go over and see what kind of chart it has what. So load and recruitment. Recruitment of what? Recruitment of your muscle fibers, right? Also load. If you're not carrying a load, it's a lot easier to move your muscles, right? So no load or very light load is very easy to contract the muscle. If you try to carry a heavy load, makes things more difficult. Okay. Oh, and here's another question. A muscle contraction without change in load, okay, increases in strength up to a point because what happens here? So constant load and a lot of muscle contraction. It is so quiet. Consult your friends. Ooh, a lot of people got it right. So here, recruitment of more motor units that is going to respond to a strong stimuli. Oh, okay. So here, adaptation to exercise. This is one of my favorite slides. But why? Because this is my friend Lucas DeSantis, with his little daughter. Melanie is her name. She's like 4 now. Yeah, he's Brazilian actually. I was teaching him some English. He has a very heavy accent, but the sweetest guy can ever meet. And he is very much into bodybuilding. Okay, I mean, hello, of course, right? And he actually won the 2018 Arnold Schwarzenegger competition, which was really cool, you know. Anyway, he is in his 40s now in this picture, and he makes sure that his muscles do not atrophy. So he's like a gym rat. I mean, he's always, every time in the gym. And as you can see, he's influencing his little daughter too, right? So endurance exercise, that tells you that you have to have a lot of resistance to fatigue, right? So endurance exercise is aerobic exercise, and the more you do of it, the more conditioning you can get to your muscles. And what happens is that you might convert some of those fast glycolytic fibers that are very prone to fatigue, you might convert it into fast oxidative fibers that can keep you going for a long time without getting tired, right? Examples of this exercise: okay, jogging, swimming, and biking. These are all types of aerobic endurance exercises. Okay. Now, this other type of exercise is resistant exercise. This is the one with the weights, right? That's my friend Lucas here, right? So this type of exercise is typically anaerobic, right? You imagine when you are pulling those weights, you're contracting the muscles so hard and you're constricting the blood vessels that are supplying the muscles. You're gonna get fatigue. Oxygen can't get there fast enough because it just can't, physically can't. You're constricting the blood vessels, right? So it's only the time that you relax and you take a break that blood can replenish the oxygen to the muscles, right? So that type of resistance training is mainly anaerobic. And when you do that very often, yeah, I know I'm blowing the time here, you might convert some fast oxidative fibers into fast glycolytic fibers, okay? This type of exercise leads to muscle hypertrophy. That's what we call this thing here. I mean, you can have a whole anatomy class on muscle just by looking at him. He has every defined muscle you can even imagine, okay? Muscle hypertrophy. Now, oh, you want another question before you go? All right, last one. What type of exercise can convert fast oxidative fibers to fast glycolytic fibers? Your answer here is A, resistance exercise. That's the weightlifting. All right, so the test is going to cover until here, and happy studying.